Oh, graphing E fields. Or graphing E fields. So, how do we do it? In order to graph E fields, there's some rules that we need to follow, and we're going to kind of walk through it and kind of think about what they look like as we're doing this. So, to graph E fields, what we're first going to do is the most basic, simplest version, and we're going to move into some harder things as we go along. First, let's just start off by drawing a positive charge here. Okay, so there's a positive charge, and then over here, this will be a negative charge. They're both of equal charge, so this one will be plus Q, and this one will just be minus Q. They're the same amount, just opposites. Okay. Now, what we have to remember is if we flash back to gravity again, a gravitational field moves throughout all of space. Okay, Earth's gravitational field goes from everywhere here on Earth all the way out to infinity. A electric field is very similar to a gravitational field in that it extends from the charge all the way out through to infinity. Okay, so they're everywhere throughout space. You can't escape them. They are there. They weaken due to that 1 over inverse squared law, but they are still there. Okay. Now, gravitational fields will always point towards the masses, but in the electric field case, we are not always attracting objects. We could also repel them. So our electric fields need to move away from some things and towards others. So how do we kind of draw that? How do we do it? Well, what we do is we will think about placing a test charge throughout all of space. And what a test charge is imagine that we had a positive elementary charge, so a proton, so to speak, but that this positive test charge didn't have any mass, and we didn't have to worry about it influencing anything else. So, if I put a positive test charge right here, I wouldn't have to worry about it, forces acting anywhere else. Like, it's just a charge that sits there, but it doesn't influence anything else. How would this charge, if this was a tiny positive test charge, how would this test charge be pulled or be forced at this location? And if I created a bunch of these tiny little test charges throughout all of space, we could start thinking about the different ways they'd be pushed or pulled. Would it be like pushed away here, and would it be like kind of pulled this way, and would this one kind of be moved like this? And if we draw enough of these, we get an entire idea of what an electric field is. Okay? So the electric field is just kind of the drawing of many, many test charges, but we just draw them as lines instead. So to think about this, if we put that test charge very, very close to the positive Q, it's going to push away from it and towards the negative Q. And one of our rules that we have for our electric fields then is electric fields must start on positive charges and terminate on negative charges. So we can imagine that here there's an electric field going straight across like that. Now, something I just want to mention briefly, you'll get different opinions about this, but I recommend this just due to AP board and college stuff. Note that when I drew this, this actually started on the charge and ended on the charge. I didn't do any of this like, hey, I'm close, or like, yeah, you get the idea. No, like I started on the charge and ended on the charge, okay? Some people draw them, halfways like that, be like, yeah, it's good enough. I don't recommend that. Some people are sticklers about this, and they're like, if you draw it halfway, you're implying that there is no electric field there, or there, and that's not true. And I'm like, okay, old man, I'm going to step on your lawn now. But just to make everybody happy, make sure you're starting on a charge and ending on a charge, okay? If we continue to draw electric field lines to get a more complete idea of what's going on here, we would have an electric field kind of extend like this on the top side, and due to the symmetry of this, it'll extend like that on the bottom. Notice we're starting and terminating. At some point we kind of get some weird things going on. If we think about, what's going to happen on the back side of this, well, it's going to go out, and technically it needs to terminate somewhere. Well, since these charges are the same, we'll talk about this momentarily, we can actually think about this extending all the way out through our universe and then wrapping all the way around and bing, there it is, got it. So there's another charge there. If we want to think about charges kind of on the edge here, kind of pointing this way. We could think about them, kind of moving out and then wrapping back in a far distance, okay? And even things at the 90-degree here, they'll actually be moved up, and they'll kind of curl, and then maybe we won't see them terminate, or maybe we will in this case the way I drew that. Maybe I can draw that a little bit better. Maybe they're like way out here, and then they come back in like that, right? So then maybe they're coming like way out, and then they come back in. That's fine, okay? But we have a more complete idea of what the field is doing anywhere here. And if we were to put a test charge on a field line, it would move along the field to the other thing, along being as best as I can draw that, okay? And if you were to put a test charge here, it would move along that field line that way. So that's what the electric field is in general. That's what we're looking at here, okay? A few other notes about the electric field before we draw some more complicated scenarios. Note, because these charges are the same magnitude, yes, they're opposite, but they're the same magnitude, they have the same numeric quantity, Q and Q, the same number of field lines will be generated, or starting, on the positive, what do we have there, 8, as will terminate on the negative, 1, 2, 3, 4, 5, 6, 7, 8, okay? We'll show in just a second that if we had, for some reason, this was like negative 2Q, it was twice the magnitude of charge as the plus Q over here, well, we would need twice as many terminating lines on the negative 2Q. So we'd have to bring in lines out from infinity. We'd have to draw it a little bit different in order to get that. Okay, so you need twice as many lines. We'll show that. So we'd have like more lines coming out from infinity. So 1, 2, 3, 4. And it's kind of hard to draw them in here because they'd have to start here. So then I'd be like 5. Where did I draw that? 6, 7, 8. So I just drew 8 more, and now we have much more going on there. Okay, so it's got to get its charge from something else. It's pulling electric field lines from somewhere else because it has double the amount of charge as this. And it's really just, if I accidentally drew 10 lines on the left one, then I would need 20 on the right one. So it's kind of a proportionality thing. It's just kind of how you draw it. The other thing with electric fields that is very important is the electric field density gives you an idea of how strong an electric field is. So let's talk about that by drawing a slightly different picture. Let's draw in this case a positive charge and a positive charge. So what would the electric field look like for this? Well, if I think about test charges, if it's very close to the left side here, it's going to push out, but as we get closer and closer to the center, we can think about, the forces are equal and opposite interactions in the center, and if something was directly in the center, it wouldn't move anywhere, which would mean that like the electric field, the accelerating field, is 0. So what actually happens here is as you come across, these are actually going to tail up. And if we were just slightly down from this, they would tail down. And what we generate here is there's this nice dead zone in the middle where the electric field is 0. And this isn't a perfect drawing representation of that, but the electric fields are not perfect that we're drawing. We're trying to get an idea of what's going on. But you can see here in the center where I drew that yellow highlight, there is no electric field line there. So if we were to consider what is the density of field lines here, the density is 0. The lines are not packed very close together at all. There are no lines, so the electric field is 0. But if we look at an edge here, there are a lot of electric field lines there. So we would have a much stronger electric field in that same kind of box region. So the number of lines you have in a tiny region, the more densely they're packed, gives you an idea of the field strength. So just like in general, if you had lines that were spaced very far apart like this, that would be a low field strength, but lines that are very close together, that would be a very high field strength. Okay. Now if we kind of finish out our diagram here for this positive set, we'd kind of get something going like this, and then going out like this. This would kind of want to be pushed up, but also be pushed away from the right charge, so it'd kind of be doing something like that. And we could just kind of swing. This goes directly left, and this one goes directly right. And then we mirror this on the other side, drawing as best as I can to get the idea. Okay, and that's just what's going on there. It's nothing too crazy, but you're just thinking about, you know, if you had a test charge there, how would it move? And once again, you can see, you know, like out in this, see how there would technically be an electric field there, because we could imagine us drawing more lines through this, but see how they do begin to spread out through these regions. They do get farther apart as we're doing that. That means, you know, as we move further out into these spaces here, the field lines are decreasing, whereas if I drew that same box like back here, these lines are closer together, a larger electric field. Okay? So there is a positive negative, here is a positive positive. If we had some arbitrarily difficult to draw like 3-body system or 4-body system where, you know, we've got a bunch of charges there, it gets kind of complicated to draw that, but with a computer you could do it fairly easily. In terms of like having the computer solve that for you, they do get kind of more complicated to draw as we go along. What I would like to do though real quick is show you this. Something that's very important about electric fields is that if we have a conductor, something that will conduct electricity, the kind of opposite of an insulator. If we have a conductor, electric fields cannot be drawn through a conductor. That is a no-no. So let's imagine for a second I have, let's imagine I have kind of like a shell, okay, where this region right here is the conductor. Okay, so this is the conductor. And let's do this. Let's on the inside, let's place a positive charge. Well, what will our electric fields look like now? Well, this is where things get a little interesting here. If we think about this being a conductor and this being the electric field, or the positive charge on the inside, we know on the inside that the electric field is going to move away from the positive charge. And it's going to move symmetrically in all the directions, so I'll just draw 8. Okay. Now, because electric fields cannot move through a conductor, I'm not drawing an electric field in that conductor space. But what about all the space outside the conductor? What's going on there? Well, if we think back to what we know about passing charges through conduction and induction and through polarization, what actually is going to occur here is, since we have a positive charge here on the inside of this conductive shell, we're actually going to polarize so that the inside of the shell now is going to be a net negative. That's because the electrons floating around in the free valence shells of the conductor can move, and they're going to move closer towards that inside surface. Okay? So the electrons have shifted inwards there. Because the electrons have kind of left the general domains of everywhere, that means we're going to have a net positive outer shell. Okay? We haven't added protons here. We haven't moved the protons because the protons can't move. It's just the electrons ran away to the inside, and because of that, they left the protons to their own devices, which nets that the outer shell here will be a net positive. Because that outer shell is now looked at as a net positive, we can say that these electric field lines are going to extend outside of the conductor like this. So even though we can't draw electric field lines through the conductor, these electric fields will still extend outside of it because we've polarized this conductive shell here. Okay, so that's an important thing to recognize. It is kind of a weird little glitchy thing, but that is what is occurring here. Okay, it occurs simply because free electrons in a conductor will never reside in the center. They will reside on an edge surface. So they'll either reside on an inner edge or an outer edge. They will never appear just in the middle somewhere. And because of that, we do not have electric fields passing through conductors. We can get up to the edge of them, and then from the other edge, out. Okay, so kind of a weird thing on that, but it is something to keep in mind. When we get into more of the AP Physics C stuff this year, we start talking about Gauss's law and whatnot, that'll make a little bit more sense of why that occurs, but that's what's going on there. Okay? That also means that the electric field inside of a conductor, by definition, has to be 0. Okay? So the electric field inside of a conductor, by definition, has to be 0. With that, that's kind of how we draw some of these field lines, though. As you draw more and more of them, you'll kind of get more of a hang of it. The big thing to remember is start at a point, start at positive, terminate at negative. Make sure you're drawing your arrows properly on the termination points, best as you can. You know, this is a probably sloppy one, kind of right up right here. That's a no-no. Bad one. Make sure that you understand that the density of these field lines designates how strong they are as the electric field. Make sure you recognize that there can be dead points in space if we have like charges here. And make sure that your electric fields inside a conductor are 0 and you're not drawing those field lines there. And if you do that, you should be pretty good. As we do more of these, you'll get better. And until next time, adios. Take it easy.